Hey everyone. Today on statistics, we're going to start looking at sampling variability and simulations of a phenomenon. And we're going to start to see how we can start to make conclusions about a phenomenon based on what we see statistically or what the results of our simulations will be. So this is all going to start with some Coca-Cola. So let's get started by looking at our Coca-Cola question. So we have, does caffeine increase pulse rate? So Ferreira and his students decided to perform a caffeine experiment. And in their experiment, 10 student volunteers were randomly assigned to drink Coca-Cola with caffeine, and the remaining 10 students were asked to try caffeine-free cola. So were their findings statistically significant? So this is good experimental design, 10 randomized into two different groups. We know already that that design is called a completely randomized design. But the thing we don't know is this whole significant, statistically significant thing. So here's what we got. In the table, it's going to show the change in pulse rate for each student. Remember, it's a change in pulse rate, final pulse rate minus initial pulse rate, along with the mean change for the group. So if I examine this here, this says that the first student who got the caffeinated Coca-Cola, his pulse rate increased by 8 beats per minute. The first student who had the non-caffeinated drink, his pulse rate increased by 3 beats per minute. Kind of down the line, this last one's kind of interesting. The person who had the caffeinated cola, this last person, his pulse rate didn't change at all, or her pulse rate didn't change at all. Whereas this last person here for caffeine, their pulse rate increased by 4 beats per minute. So that's kind of interesting that someone's pulse rate is going to increase. The caffeinated group has a mean change in pulse rate of 3.2. So on average, their pulse rate increased by 3.2 beats per minute. And then for the non-caffeinated group, their pulse rate increased by 2 beats per minute. So their pulse rate increased as well, but it didn't increase as much as the caffeine people. So find the difference in pulse rates for each group. That's easy. That's just 3.2 minus 2. So just 1.2 beats per minute. Does this initial reaction lead you to believe that you have found evidence that caffeine does or does not increase heart rate? Well, I think the evidence kind of points us to caffeine does increase pulse rate because the caffeine group had a higher increase in their pulse rate than the non-caffeinated group. Moving on to number 2. What are 2 possible explanations for the difference in mean pulse rate? Now this is the interesting part because we got to think of those 2 explanations. The first one we already have. Caffeine really increases pulse rate. Now, we're going to assume that that isn't a scientifically proven fact, and we're just going to say, well, it might not even be proven for you. You might not even think that it's true. So that's one explanation. That's one reason why the mean pulse rate increase for caffeine is greater than the mean pulse rate increase for no caffeine. That's a possibility. However, there is another possibility that exists out there. In this alternative explanation, the caffeine really doesn't have anything to do with the increase in pulse rate. It just so happened that the people whose increased pulse rate the people with more increased pulse rate happened to be sorted into the caffeine group. Because remember, this was some random assignment. So you can imagine if caffeine had nothing to do with it, maybe this 8 person would have been put into the no caffeine group, and this negative 2 person, they could have been randomly put in the caffeine group. It doesn't matter because we're saying that the caffeine doesn't actually raise pulse rate. We're saying that the caffeine group has a higher pulse rate mean change by random assignment. Okay. The randomness accidentally, I guess, sorted all of our high pulse rate change people into the caffeine group. Okay. So try to decide if that difference in pulse rate is big enough to be convincing. Yeah, that's not really a lot of pulse rate increase. 1.2. Okay. So we're going to try to decide is that a big enough pulse rate? So here's what we're going to do. We're going to gather 20 index cards to represent 20 students in the experiment. Okay, well, that's not really going to happen online. It's definitely not going to happen for you. That's going to be difficult for you to do. So here's what we're going to do instead. I've put all of the caffeine group in these, for these, their increases over here. You'll have to trust me. And when I say that, I didn't tamper with the data at all. That's actually their mean pulse rates over there. Let's try and zoom in a little bit. Yeah. So, and then the non-caffeinated group I put over here, 3.2. And then what I did was I computed the average of this first group, which is, row 2 through row 11. And then I subtracted from that the average from row 12 to row 21. I got 1.2, just like we said it would be. And then I created a dot plot, or I'll be creating a dot plot. So what's going to happen next, if we take a look here, is we're going to shuffle the cards. So I'm going to shuffle all of those. I'm not going to add any new data. I'm just going to take the data that we already have, and we're going to pretend that they were just randomly sorted that way. So if I randomly sort them again, then we should get a new difference of averages. So the thing to remember here is that, again, we're going to assume the caffeine didn't make a difference. If we assume that that's the case, then just by shuffling the cards, we'll get a new set of experimental data, because the students, in this case, they were sorted into a different group, and their change was going to be their change regardless of what group they were put in, because the caffeine, we're assuming, doesn't make a difference. So let's go ahead and shuffle the deck, okay? I'm going to go ahead and shuffle this, and let's see, randomize the range, and oh, look at that. This next, I get, oh, that's not quite correct. Hold on. No, it is correct. I got 1.2 again. That threw me off because I wasn't expecting to see another 1.2. But when I randomized the pulse rate, I got another 1.2. So I'm going to put another 1.2 here. And that should put another dot in my dot plot. There it is. And another dot in my dot plot. I'll do this one more time. Let's randomize the cards, the pulse rates. And I get negative 1.4. All right, we're going to put a negative 1.4 here. And I'm going to continue to do this a few times. I want to show you there's our dot plot now. And I'm going to do this a few times and fast forward, so you don't have to sit through the entire thing. But we'll just produce our data with all of these randomizations. As you can see, we've created our dot plot of our, of all the experimental results. And what was our what did we get from our experiment? Our experiment said the difference was 1.2. Where is 1.2? That's here, actually. This one right here. So that's going to be important to us. Let's get that dot plot, and I'm going to copy this and put it over into our OneNote. Okay, our dot plot's in place. What does each dot represent? And this is a question that we're going to be asking multiple times throughout the semester. Each dot represented a difference of means in one trial if the caffeine had no effect. What percentage of dots are greater than equal to 1.2 that we found in the experiment? Okay, so let's count. There is 1, 2, 3, 4, 5, 6, 7, 8. So that's 8 out of my 40 dots, which is 20%. 20% of the time, we got a difference of 1.2 or greater. So interpret this design, or interpret this result. So assuming that caffeine made no difference, assuming that caffeine does not affect pulse rate increase, there is about a 20% probability of getting a difference of 1.2 purely by chance. Okay, 20% now. 20% is not uncommon. Okay, uncommon in AP Stats is usually somewhere less than 10%. Sometimes 5% is what we would say for uncommon. So do you think that the difference in means we found in the caffeine has occurred purely by chance? So our percentage is greater than that 5%. So this is what we would call not statistically significant. The probability of obtaining something that is either our experimental outcome or something more extreme than our experimental outcome is greater than 5%. So we would call that experiment not statistically significant. So since it is not unlikely to get a difference of 1.2 purely by chance, this could have been a coincidence. Now, I wouldn't be a teacher if I didn't show you the other side of this. So what if the percentage is less than 5%? Since if the percentage was less than or equal to 5%, we would say that those are statistically significant findings. And that would mean that we were unlikely to get a difference of 1.2 purely by chance. So the caffeine probably had an effect. So that's our those are our two really big vocabulary for today. Not statistically significant means that things could have happened by chance because the probability is, well, in this case, 20%, but generally speaking, greater than 5%. And statistically significant means that since we get a probability less than 5%, it's unlikely to have gotten our result in our first experiment purely by chance. Here's our big ideas. Sampling variability is the concept that different samples are going to yield different estimates. We see that all the time, or we should see that all the time. It's something that we should be kind of familiar with. Depends on what sample we draw. We could get a different result or a different average, etc. The other thing with sampling variability to know is that a large sample is always going to produce more accurate estimates, everything else being equal. And then there is this idea of the margin of error. And the margin of error, which we didn't talk about in this experiment that we did today, but the margin of error creates an interval of possible values for the value of our, sometimes it's an average, sometimes it's the value of a proportion. Average is the easiest one to talk about, but a margin of error says that, okay, this guy weighs 160 pounds with a margin of error of 10 pounds. What that means is that the true weight is probably somewhere between 150 and 170. So it gives you a range of values, an interval of possible values for the actual weight. Statistical significant. That means that the results from the study are too unusual to have occurred purely by chance. Okay, we just did a simulation where we randomized things, the results, and we counted what proportion of our dot plot was. In our case, we did greater, but you could definitely do less than. In this simulation that we're looking at here, we're counting the probability of trials, or the proportion of trials that are less than a certain number. And if the proportion is greater than equal to 5, then we call that statistically significant. Sorry, I misspoke. If the proportion of dots is less than equal to 5, we call it statistically significant. If the proportion of dots is greater than 5%, then we say it's not statistically significant. Let's take a look at these questions down here for the check your understanding. So how much do National Football League players weigh on average? In a random sample of 50 NFL players, the average weight is 244.4 pounds. So do you think that 244 pounds is the true average weight for all NFL players? Explain. Well, taking that sampling variability to heart, all samples are different. So it's unlikely that the true weight of NFL players is 244 pounds exactly. We never expect the sample mean to be precisely equal to the true mean. But under most circumstances, we expect it to be close to the true mean. Another sample of NFL players was taken. Would you expect that to be 244 pounds? Well, every sample is going to be a different group of NFL players, so the sample mean is going to be unlikely to be the same as 244 pounds that we found from the previous sample. But it's probably going to be close. Estimates are usually given with a margin of error. The margin of error for the estimate of 244.4 pounds is 14.2 pounds. Based on this, would you be surprised if the true average weight was 260 pounds? If we accept that margin of error to be true, then the true average weight of NFL players should be between 230.2 and 258.6 pounds. Now, where did those numbers come from? Well, let's see. Over here on the side, let's calculate 244.4 minus 14.2. And look at that, 230.2. And so what do you think we get if we do 244.4 plus 14.2? And you guessed it, 258.6. So the true average weight should be between 230.2 and 258.6 pounds. So if the true average weight was 260 pounds, then that would be surprising because it's outside that margin of error. Okay. The margin of error tells us a likely range of values for the true average weight. Lastly, which would be more likely to give an estimate close to the true average weight of NFL players? A random sample of 50 players or a random sample of 100 players? Explain your answer. So a random sample of 100 players is likely to yield an average closer to the true average weight, since large samples produce more accurate estimates. So that's the end of us for today. We have looked at this one simulation. Hopefully it made sense to you. And then we started talking about statistically significant, which is a big portion of what we're going to be doing in the future of AP Statistics. So I'll see you next time when we well, when we do more AP statistics, and see you until then.